Hello, Physics 2. So, this is it. This is the chapter. This is what you came for, to bring it all together. See Maxwell's equations in all of their stunning glory and beauty. So, of course, I have no permission to use this song on YouTube. Don't turn me in for a copyright violation. But that is, of course, Rihanna's and Calvin Harris's This Is What You Came For. All right, so chapter 23. This is what you came for. The rubber is going to meet the road. The road and the beauty of the classical model of physics will be on full display. Maybe I'm hyping it up a bit too much, but seriously, I think this stuff is really cool. And that's not an act. Whether or not you feel the same way, well, we're in different fields. It's okay. Okay, so we are finally going to get to see all of Maxwell's equations in their true form. We can complete them. And what you do with them, you can either think, oh, that's a cool thing I learned. You could take this and take a class on electromagnetism. You can take a class in optics, which we will be offering in about 2 years' time. You see Maxwell's equations again there. They're just incredible. And you get to see how modern physics actually came out of them. So if it wasn't for all the work that was done in the century before Einstein, Einstein would not have had the opportunity to develop his theories of the photoelectric effect, general relativity. All of these have built on this. Which is always true in physics, that we build on each other. But I hope that you at least leave with some appreciation of what this research has meant, even though it is old research. But it is good. Is good stuff. All right, so Maxwell's equations describe possible spatial patterns of electric and magnetic fields in space. And we're going to complete them in the integral form. And I'm going to show you the differential form because, it's me. All right. So, to complete them, we need the Ampere-Maxwell law. So we know about Ampere's law, but it's not complete. All right, so if you recall, Faraday's law shows the relationship between the change of the magnetic field, a change in magnetic field, and the Curly non-Coulomb electric field. So dB dt not zero, then you have a Curly non-Coulomb electric field. What we have not actually talked about yet, have not looked at, is when there is a changing electric field with respect to time. What exactly happens when we have a changing electric field with respect to time? So, to complete the Ampere-Maxwell law, we're going to need to bring that in. So, we need to see what happens. All right, so presently we know Ampere's law. So B dot dl, that's that path integral we've seen before, is equal to mu naught times the sum of the current enclosed. So basically this is where we walk around and we pick up all the little currents and we add them up. Okay. What we need to do is we want to, so what if we apply Ampere's law to a circuit containing long straight wires charging a capacitor. So we've seen several examples of capacitor circuits, from RC circuits to LC circuits. So they exist, they're real. So we've got our field in the capacitor. We've got the current on either side. And then we know, so let's do a side view now. So we know that there's an electric field. We know that there's a magnetic field going around it. We know if the current is changing, that magnetic field is changing. So I've already kind of hinted at this, but let's start thinking about it. So what is changing? So the magnetic field is changing, therefore minus dB dt is changing, and it's changing because the current with respect to time is also changing. And remember, that electric field with respect to time is also changing. They're all changing. All right, so let's see how we can use this to understand Ampere-Maxwell's law. So, to apply Maxwell's law, to apply Ampere's law, we need to choose a path. And so what we could do is we could say, okay, well, we know that all the change is happening in here. I know there's a magnetic field. All right, so let's choose a little circle, do a path right here. And we're just going to walk around and pick up currents. So let's see, we're walking around looking for currents to pick up, and wait a second. So there's a current here, there's a current here, but they're not in our path. We can't pick them up. We can't do Ampere's law. So basically, we've learned that there is no current enclosed in this area. I mean, which makes sense, but something is going on. It is interesting. What is it? So basically, what we have just learned is that B dot dl for this situation is equal to mu naught I enclosed, which is equal to 0. Okay, well, that's kind of dull. And, you know, I did just put this list of all of this stuff going on. So we need to be able to think about how to go after it. All right, so I've got an idea. Okay, we're gonna take this, do the side view again. And you know what? Okay, so we've got our magnetic field. There it is. And, what if we do something that looks like this? Little bulging out. Okay, so in this case, B dot dl is equal to mu naught I. So this is very different than our first example, which kind of implies that there was a zero magnetic field. But that just seems, there's no current enclosed, and is there a magnetic field? That just doesn't seem to make sense. This makes more sense. I mean, this is in line with what we know. I mean, we know there's a magnetic field around a capacitor. We've talked about it. So we expect a magnetic field. We expect a B field in the capacitor. I mean, we could measure one. We could put a compass up next to it. I mean, and also we know wires produce B fields. So clearly, this is what I mean by this equation being incomplete. We've got something weird going on. Well, so let's start pulling together stuff that we know. I mean, we've learned a lot this semester. It's been a journey. Now I just have songs stuck in my head. Life is a highway. All right, so Chapter 17, Biot-Savart. That's where we got the magnetic field of a long straight wire. So the magnetic field of a long straight wire B is equal to mu naught over 4 pi 2I over R. R is the distance from center. Okay, and we would expect B because, you know, let's draw this. So we've got, here's our capacitor. Let's draw some B fields in orange this time. I mean, only a small chunk of the wire is missing, so maybe a little weaker, but small piece missing. So should still be a B. So maybe B dot dl is approximately equal to mu naught over 4 pi 2I over R times maybe 2 pi R is equal to mu naught I. I mean, that makes more sense because, you know, here we've got our B field. Got a nice little dl and this 2 pi r. I mean, that would make more sense, but Well, let's everybody give applause to James Clerk Maxwell. Thank you, Maxwell, because he recognized there was a problem here. And so he came to the rescue. So James Clerk Maxwell. And you thought Captain America was cool. All right, so Maxwell suspected that there might be a relationship between d dt not being zero and a magnetic field. So, current running through an area is not everything. Perhaps if changing magnetic fields with respect to time cause curly electric fields, maybe we get a magnetic field from a changing electric field. All right, so interesting. Let's look closer. All right, so let's recall electric flux. So electric flux is equal to E dot n hat dA. And so if we look at the capacitor, we know we've got an E field, so maybe if we're splitting it here, then, and so inside the capacitor, the electric field is parallel to n hat, so we have E is equal to Q over A over epsilon naught, something we've seen many times before. And then of course we also know, I'm going to write this down again, outside the capacitor, the electric field is small. So you have a fringe field outside the capacitor. And this is especially true if the plates are very large and they're very close together, which is true for most capacitors. So basically there's no electric field outside that is worth thinking about, and a lot of electric field inside. Okay, so let's put this all together. So electric flux is equal to Q over A epsilon naught. A cosine of 0 is equal to Q over epsilon naught. Okay, good. All right, so we still need to account for the change in electric flux. So we have flux, but not the change in flux. Okay. So the capacitor are charging to Q. The capacitor is charging, and Q is changing over time. Over time, related to the current. So we have delta Q is equal to I delta T. And from here you get dq dt is equal to I. Seen this several times now. So now we need to think about the time rate change of electric flux. Okay, so we're going to start to put this all together. So the change of electric flux with respect to time, so we're going to have d dt q over epsilon naught is equal to current over epsilon naught. Okay. So then I, current, is equal to epsilon naught times, the change in electric flux with respect to time. There was a current there after all. And this has units of amperes. And by the way, how I walked you through thinking this is a really good way to reason through physics equations. And if you are someone who is a conversational learner, I would actually recommend talking it through. If you're not, there's other methods that work, namely you start manipulating equations, plugging in known expressions, and you start trying to move towards what you want. But that can be a really just valuable way to derive what you don't know. And this advice goes beyond the advice that I would give for passing a standardized exam. All of you are going into technical careers. And so sometimes you're going to encounter things where you may have to derive something, whether it's for the field of medicine or dentistry or something else. And this is a way to do that and to convince yourself that some paper you've read has worked, that some new theory has worked out. So this is, sometimes I'll indicate this is very useful for an exam, and sometimes something is very useful for a broader career. This skill has brought me a lot in life, and it's something that I developed over studying physics. Okay, so tangent aside, we're still not done. So we can combine this with our present expression of Ampere's law and get Ampere-Maxwell. So B dot dl is equal to mu naught times the current enclosed that we already know about plus epsilon naught times change in electric flux with respect to time. So standard current related to a change in electric flux, where the electric flux is equal to the integral we've seen before. The electric field times n hat dA. All right, so now we finally have the full expression. We have a full expression that handles changing electric flux and incoming or outgoing, for that matter, current. Basically, and in words, Ampere-Maxwell says there is a magnetic field associated with a time-varying electric field. And all of this leads us to Maxwell's equations, which I'm going to put on a new sheet so they can just be all shiny and exciting. So they do come in different forms, so this is the integral form. So E dot n hat times A, or dA, is equal to 1 over epsilon naught Q enclosed. Is 1 over epsilon naught times the sum of the Q enclosed. This is Gauss's law. Then you have B dot n hat dA is equal to 0. Consequence of the lack of magnetic monopoles, Gauss's law for magnetism. Then we have E dot dl is equal to minus d dt. B dot n hat dA, which is Faraday's law. And then we have our shiny new one, well, new to us. B dot dl is equal to mu naught times the sum of current inside plus epsilon naught times the change of electric flux. And this is Ampere Maxwell's. And there you go. There they are. These are some of the more fundamental equations that we learn in Physics 2. Now, I'm sure you're curious about the differential form, and I promised you that I would show you that. So let me do that. So I won't ask you to do any manipulations with the differential form, but it is actually the way that we tend to memorize them in physics, and then we promptly forget them because we don't like to memorize things. So here we go. Nabla dotted with E is 1 over epsilon naught rho. Nabla cross E is equal to minus dB dt. Nabla dotted with B is equal to 0. And Nabla cross B is equal to mu naught J plus mu naught epsilon naught del E del T. And there you go. Maxwell's equations. And so one of the things you get to do in an E&M class is you will use these equations and you will test different wave functions to see if they satisfy the criteria. And you get to solve them for if a magnetic monopole existed. So yes, they would still work if we ever discovered one. We won't. All right, so we can also say the net electric and magnetic force so we have F is equal to QE plus QV cross B, where the change in force is equal to I dl cross B. So currents. And there you go. All right. I think we'll end part 1 of this lecture right here. And I'll see you next time for part 2.